And we're back. Welcome back and happy Tuesday. Today we will continue on in our discussion of inference, specifically method of moments estimation. But before we begin, some administrative bits. The reading has changed in Chapter 9, Sections 9.1 through 9.2 on method of moments, pages 238 through 247. Why don't we continue on? When we last left off, we talked about the moments and where they came from tools from physics. And at the time when statisticians were creating moments, or talking about rather the shape of distributions, they had available at the time the tools of physics. And so before we can talk about method of moments, we have to talk about what a moment is: a force at some distance, force times distance. And so we have the general form for the so-called nth moment, mu sub n, and it depends on whether or not you're dealing with a continuous distribution or discrete distribution. If it's a discrete distribution, we have the sum. If it's a continuous distribution, we have the integral of the distance from a pivot, x minus that pivot c, raised to the nth power. That's what makes it the nth moment. And we multiply by the force, thinking of that probability mass as exerting a force when subjected to gravity. And so we add all of them together, and that gives us the nth moment. And of course, we say this moment is so-called centered about origin if that center point, that distance from that pivot point, is equal to mu, the mean, or we center about a balance point, non-centered, if that pivot point C is equal to 0. And we talked about the first moment, second moment, third moment, and fourth moment. The only difference is what that exponent n is. And so here in this case, we have mu sub 1, mu sub 2, mu sub 3, and mu sub 4. And of course, some of these moments you've seen before. The first moment is the mean. It's non-centered. Second moment, centered, is the variance. Third moment, centered, about origin, is called skew. And the fourth moment is kurtosis, a measurement of flatness. So why don't we continue? And so here we have an example of a moment from physics, and we'll depict the third moment. Now in this, we have a mass at 2 meters from the pivot, the center, and this mass exerts 10 newtons of force. There's another mass that's 1 meter from the pivot on the other side of the seesaw, and it exerts a force of 20 newtons. So if we compute the moment, we take that negative 2 meters, because it's on the left-hand side of origin, or the center, and we take negative 2, we exponentiate it to the third power, because it's the third moment, and then we multiply by that 10. Okay? And then for the second mass, the mass on the right-hand side, we take that distance times the force, so that's 1 raised to the 3 power, so because it's the third moment, and we multiply by 20. So if we do this for this system, we get negative 2 cubed is going to be negative 8 times 10. That's going to be negative 80. Let me set my pen. And that is going to result negative 80 on the left-hand side of the pivot, and we get positive 20 on the right-hand side of the pivot. The resulting sum of those moments is minus 80 plus 20 is negative 60, and it's going to be lopsided. So that means we're going to have a net force of 60 in this direction. Okay. And so here we know that this particular seesaw board is going to be lopsided. It's going to lean to one side. And this third moment tells us that it is lopsided and how much it leans to that one side. All right. So let's take a look at this example. And so we're going to put equal size masses on the left-hand side and the right-hand side of that board. And these masses are going to be at different distances. On the left-hand side, it's going to be 2 meters away. On the right-hand side, it's going to be 1 meter away. So again, we sum the moments relative to this 0 point. We get negative 2 cubed for this mass on the left-hand side. And we multiply by 10, 10 Newton meters. That's going to be negative 80. And on the right-hand side, we have 1, because it's 1 meter away, and that's going to be 10 is the force. Negative 80 plus 10 is equal to negative 70. And so because it's negative 70, we know it's going to be lopsided, and it's going to tip in this direction at a moment of 70. The sum of the moments in this case is negative. All right. So in this case, we have two masses that are the same on each side of the board, and they exert the same force, 10 newtons, but because one is further away, that moment is going to be bigger than the one that's closer. Okay. And so here, let's change the scenario, and we have the same masses, therefore the same force, at equal distance from the pivot. So on the left-hand side, we have a 10 Newton force from this mass, and it's at 1 meter from the pivot. On the right-hand side, we also have a mass that's exerting the same 10 newtons, and it is 1 meter from the pivot on the right-hand side. So we take that minus 1, cube it, that's negative 10 for the contribution to the sum of the moments for the left-hand side of the pivot, plus 10 for the contribution on the right-hand side. We add that up, it's 0. So the sum of the moments is equal to 0. And what that means is that the board is going to balance because we have equal moments on both sides of the board, force times distance. All right. So that's just a demonstration relating the moments to the skewness as it pertains to the third moment, relating it back to a physics example. So let's take a look at method of moments estimation. We talked about moments previously. Let's generalize to the so-called case population moment. Now, there are two different categories or classes of moment. There's a so-called population moment, but there's also the so-called sample moment. And the population moment is called the population moment because the probability that governs it is that unknown ground truth population probability. And so the population probability for the case moment or the case population moment, it involves an expectation, but it's an expectation with respect to that population distribution. And so we have mu sub k, the case population moment, is equal to the expectation of our measurement, random variable x raised to the kth power. All right. Now, if we were to expand this out, it's just the sum for discrete distribution, and if it's continuous, it's an integral, of the measurements, xi, exponentiated to the kth power, times the probability of that xi random variable taking on certain values. Now, there's also the case sample moment. And the case sample moment we denote as m, and that m is subscripted with a k, and that k represents the exponent. And so m sub k, the case sample moment, is 1 upon n, the sum of xi to the kth power. Now, of course, with samples, the assumption is that each one of these values, xi, is equiprobable, and therefore has a probability. You can think of this as 1 over n. And so this is our case sample moment. And so the case sample moment is going to do, we have estimates, mu sub k, from some sample, and we're going to use the sample moment and use this population moment to solve for an estimator in closed form, some formula, statistic, over the data that we can use as a reasonable replacement for our population parameter. And so we know that the first sample moment is the same as the sample mean. And if you raise this k, or treat this k as a 1, that's the first sample moment, we get m sub 1 is equal to 1 upon n times the sum, I goes from 1 to n, of all of the xi raised to the 1 power. That's just x bar. So the first sample moment, that's non-centered, is exactly the sample mean. Now, of course, if we wanted the kth moment for k greater than equal to 2, where it's a centralized population moment, meaning that you're going to subtract the mean, that c value, that pivot, is going to be the mean mu. Well, we would denote, and this is the convention the book uses, we denote the fact that this population moment is centralized when we have this apostrophe here. So mu apostrophe sub k is the kth, there's the k, that relates to the exponent, the kth population moment, that's the mu, and it's centralized, meaning that you subtract off the mean, so you shift that distribution to be centered at origin, and we have that apostrophe to represent the fact that it's centered. And so mu prime sub k is equal to the expectation of x minus mu1, where mu1 is the first population moment, that difference exponentiated to the k power. And so if we expand that out for discrete distribution, that's just the sum for each of the measurements xi, random variables, minus mu1, that difference, quantity, to the kth power, times probability of xi. So this is our distance, and this is our force, as we talked about in the previous few slides. And so if we look then also at the kth sample moment that has been centralized, by the naming convention in the book, we use this apostrophe to denote centralization. We take our mk, our kth sample moment, and we centralize it. So we subtract off x bar, and x bar is the first sample moment. So we know the kth sample centralized moment is m prime sub k is equal to 1 upon n, the sum, quantity, xi minus x bar, all exponentiated to the kth power. And so we know that we can compute an estimator for our mu k population moments from a sample. How do we do this? Well, let's look at some other moments. The population second central moment. So it's the second population moment. So we're going to have mu sub 2, and it's centralized. So we're going to say apostrophe. That's just the variance. So mu sub k, mu prime sub k, is the same as what we're calling sigma squared, which is just the sum of the difference between each one of the measurements and the mean, quantity squared, weighted by the probability. So this is just the distance squared, and this is the force. And so it's centralized because C is equal to mu, which is also mean, or the first population moment. And so here we have the second central moment is exactly the variance as we had been studying before. The sample second central moment is the following. That's just our s squared. Well, this particular s squared is biased, but you can certainly transform this to make it unbiased. And so the second central sample moment is m prime sub 2. Prime means that it's centralized, 2 means it's the second, m meaning that it's the sample, is 1 upon n, sum of the difference between each of the measurements xi and x bar, which is the first sample moment. This is our distance, and you can think of this as your force. And so that's just our s squared, the biased version. And so the leading coefficient is 1 upon n, because this is our formula for the second central moment. And it's not 1 upon n minus 1. It means that it's biased versus unbiased. And to make this unbiased, we would change this leading coefficient to 1 over n minus 1. All right. And so what is method of moment estimation? It's a simple idea of literally matching moments. And which moments do you match? Well, you match the population moment with the sample moment. So you match the first population moment with the first sample moment, the second population moment with the second sample moment, and it gives you a system of equations that you then solve for the unknown, and it gives you a formula, a statistic, a function in the form of a function over data that you can use as a reasonable replacement for an unknown population parameter. And so there are many distribution families, things we've talked about. We've talked about Bernoulli, binomial, uniform, Poisson, exponential, gamma, negative binomial, and the normal distribution. We talked about a lot of stuff in stochastic last semester. And so when you have a data problem, you enterprise first to ask, well, which one should you use to describe some data phenomena that arise? And so each of these families of distribution has its set of parameters, and these parameters for the distributions govern their behavior. And so you start out by choosing the distribution family whose properties most closely match the properties of the data. And these properties are described as moments. And so, for example, the Poisson distribution, we know it has a parameter lambda, the rate parameter, and a different instantiation or value of lambda is going to correspond to a different Poisson distribution. And so if you want to deal with the properties of a distribution family, you're going to deal with its moments. All right. And so that kind of makes sense because the moments talk about the shape of the distribution. And the shape talks about where they place more probability mass and where they place less probability mass. So a good descriptor of a distribution is its set of moments because it's describing different aspects of the shape, the central tendency, the dispersion, the skewness, the flatness, and so forth. And so if you want to estimate k many parameters associated with the parameters of a distribution, and they all have different parameter counts, the normal distribution has 2, the mean and the variance. The Poisson has 1, the rate parameter lambda. So you want to estimate then k parameters that you can use as substitutes for the unknown population parameters. And you do so by equating the first k population moments associated with that distribution with the first k sample moments, and then solving this system of equations you are given. And so let's imagine then you observe some number of events that occur during some and many windows of observation, so they're occurring in time. And you believe that the underlying distribution, you make an educated guess based on the structure of that stochasticity, you guess that you think it is a Poisson distribution. And so what do? You equate then, knowing that the Poisson has 1 parameter, you equate the first population moment, mu sub 1, there's our mu sub 1, with the first sample moment, m sub 1. Well, we know m sub 1 is equal to x bar. That's exactly what we said a few slides ago. And then we know that the first population moment is e of x, that expectation. Now, expectation of x for Poisson distribution, we know that e of x is equal to lambda. And so now you get an equation, and this equation is of the form lambda is equal to x bar. And so now that you're done with this procedure, you say, if I want to know a formula over data, function over data statistic, that I can use as a definition for lambda, well, I'm going to use x bar. And that's exactly what our solution is. And so now you call this thing an estimator and for lambda. And an estimator for lambda is noted as lambda hat. Hat means I am an estimator of, and then the symbol underneath the hat tells you which population parameter this thing is an estimator or reasonable replacement for. And so this reasonable replacement for lambda, or lambda hat, is equal to x bar, which is just x1 plus x2 ... plus xn over n. And that's going to be our x bar, which is precisely a function over data. And so this type of estimator lambda hat, in this case, is called lambda hat MME, and where that MME stands for Method of Moments Estimator. And that's a hint to the reader to describe to you the procedure that was used in order to get this particular statistic over the data as a reasonable replacement for lambda, the unknown population parameter. And so here we have lambda hat MME is equal to X bar. And we got this by equating the first population moment with the first sample moment. And the reason why we only did this for the first, because we know that the Poisson distribution only has a single parameter, lambda. If it had two parameters, we'd take the first population moment equated with the first sample moment, and then we'd take the second population moment equated with the second sample moment, and then we'd have two systems of equations for which we'd have to solve for the unknown. And that's going to give us two estimators. All right. So with that, that's all I had. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.